Artyom Sharov, who was an intern in our team, and he just completed his PhD in the Technion CS department, and also with Arif Merchant and Murray Stokely. So just something brief about our team. We are a small research team focused on storage systems. So we analyze and try to optimize Google storage systems. Here's some things that we've done in the past. We're trying to understand the workload and the health of the devices. For example, there was a paper in FAST this year that was a collaboration between our group and Bianca Schroeder. There was a paper in OSDI 2010 about understanding server failures in Google's data centers. We also work on more upper level storage, for example, caching in file systems. And I'm going to talk about data placement for distributed transactional databases in this talk. But in this talk, I'm going to assume that the sharding of the database is fixed. We have another work that which we are trying to optimize the sharding in a dynamic way as well. That is under submission. We also recommend to the management what make recommendation about future storage directions and some other things. So in this talk, I'm going to assume a very common storage model where you have a transactional database that is sharded, and each partition is separately replicated, potentially across one. So the orange here is one replica, and it's replicated potentially all over the world. Some of the replicas have a special role. They vote on commits. For example, if, in Paxos, you may be familiar with acceptors or followers and Zookeeper. So these are the blue servers. They are voters. And one of them is the leader. It coordinates the replication. It does things like locking, transaction management, and so on. And then there are, of course, clients all over the world. This database that I'm going to talk about, it has an API for single key reads with various consistency guarantees, and also for single and multi-shard transactions. So what are we doing here? We are trying to optimize the replication of the database for operation latency. We're trying to do that dynamically as the workload changes, and as the so we're trying to adapt the replication to the workload and to the network conditions. We have 3 levels of optimizations. First is how many replicas do we need and where should they be located. Second is which replicas should vote for commits, and which should. So the other replicas that don't vote, you can think about it as learners in Paxos, or replicas that passively learn about committed state only after it's been committed. And the third one is which of the replicas should be the leader. So I'm going to do this in the reverse order. I'm going to start from the leader. But before I'm going to talk about how we optimize the leader location, why is it important at all? So suppose that this guy here is the leader, and now we have a client in Israel and client in the US. And the Israeli client invokes a read operation. It contacts, we call this boundedly stale read. It contacts its closest replica in Italy and says, I want to read some piece of data, but only if it's up to 5 seconds stale. And that replica sees that it doesn't have data that is as fresh as needed, so it forwards the request to the leader. Obviously, the location of the leader matters here a lot for the latency of the request. And here's the client in the US sends the commit request to the leader. The leader sends a commit message to all the replicas. And in our database, specifically, it's a quorum protocol. It is, unlike the previous talk, it is a synchronous replication over one. Synchronous, not asynchronous. And we have a quorum protocol to be able to handle failures. So here what we see is that intuitively, the leader must be close to the clients, but at the same time, it must be well connected with the other replicas so that the commits are fast. So that is what we're going to try to do. So what are the common ways to do that? Usually people use heuristics such as place the leader close to the writers. For example, in Yahoo Peanuts or in Megastore, that's what they do. Also, there is a heuristic called fastest quorum, which is pick the replica which can gather the quorum of responses the fastest to be the leader. The problem is that both of these ignore reads completely. And in our system, most of the databases were read heavy. Closest to writes ignores quorum latency. It's possible that you have a very close replica to the writes, but it's very far away from the other replicas. So it's not going to help. And the fastest quorum ignores client locations. So you have a fast quorum, but in a very remote location distant from all the clients. And random. This is actually what we had in our system previously. In this policy, the group leaders are, the shard leaders are chosen randomly among the voters. Obviously, this does not consider the workload at all. Okay, so in this level of optimization, we assume that we have a fixed set of replicas and locations, and we know who the voters are, and we're just trying to pick the best leader out of the voters. We are trying to optimize for average latency, and in the paper we talk about tail latency as well. So we look at the clients, and we group them by their locations. So we call each location a source location, and we also distinguish the different operations of the database. Now, what we want to know two things, basically. One is the rate of operation type op from location source. And fortunately, we have that, because Google has a global monitoring infrastructure. So we know how many operations of each type are invoked where. So that's good. And the second thing we need to know is the latency of operation type op from source given a leader in location L, where L is one of the voters. This we don't know, because the monitoring infrastructure only monitors the current leader, right? The situation, the latency is with the current leader. Whereas we need to know what happens if we change the leader. So how do we do that? We use the network round trip times, which are monitored, cross one, and we use our knowledge of how the operations of the database look like. So here's an example. This is the leader again, and the Israeli client invokes a read. The read goes to the closest replica, and then to the leader. So the average latency of this operation, given a leader in this location, is simply the average round trip time between the client and its closest replica, and the average round trip time between the closest replica and the leader. And since we're talking about average latencies here, we use the linearity of expectation. This does not work for tail latencies. For tail latencies, we need to do something more complicated. For commit, the client sends a request to the leader sends a request to everyone and waits for a quorum. The latency of this operation is round trip time from the source to the leader, plus the leader's average quorum latency. In the paper, we show 5 different operation flows and how to compute this for them. For average operation latency, we basically want to minimize the weighted average, where the weight is the rate of the operation, and the latency is what I showed you. We do that, we compute a latency-based cost for every potential leader and pick the leader with a minimum cost. We can consider all the operation types or just some subset of interest. For example, just the transaction or just the non-local operations, and so on. And we need to do that dynamically, obviously. So we divide time into time intervals, and we use exponentially moving average to consider multiple intervals in the history. So here's an example of how this works. The x-axis is time. We use a day worth of workload from a real database. It's half-an-hour intervals. And y-axis is the latency overhead over the optimum. The optimum is 0 here. It is computed by having an oracle that looks at the time interval and after the fact tells where the leader should have been. So the optimized is what the recommendation we produce. You can see that it's indistinguishable from the optimum. The random here is the green one. It's about 60% worse. And the fastest quorum is even worse. Simply because in this specific database, there are very few operations requiring a quorum. So it doesn't really matter if the quorum is very fast. Here's a production graph. This database was using a random placement up to here. And at 4 o'clock, we activated our system, and the leaders started migrating to their right location. The y-axis here shows what percent of the leaders of the database. There are many shards. Each shard has a leader. What percentage of the leader migrated to the right location? So we can see that as all the leaders migrate, the latency drops. And the latency here drops by 70% and stabilizes at about 60% improvement. So overall, we saw that for about 20% of the databases, we can improve latency by more than 50%, compared both to heuristics and to random placement. So in our system, actually, users can hint the system or where they want the leader to be placed. Only a small percent of the users do that, about 20% or so. And we saw that most of the time when the user gives a hint where he wants the leader, he knows what he's doing. But in about 20%, he's wrong. In those cases, we can also improve. But again, this is a small fraction of the users that even try to optimize it by themselves. We saw latency improvements as much as 94%. And maybe surprisingly, we got better improvements for commits than for reads. And we investigated this a little bit and saw that actually the writers, the committers, tend to be more concentrated. So it's easier to optimize for. Whereas the readers tend to be more spread out. So if you improve something for one reader, you make it worse for another. Okay, so the next optimization tier is how do we choose the voters in addition to the leader. One of the motivations for this was this something called follow the sun idea that many people talk about. The idea is that if it's daytime in the US, that we expect most of the rights to come from the US, and then you want the voting to happen in the US, whereas when it's nighttime in the US, daytime in Europe, you expect most of the rights to come from Europe, and you want the voting to happen in Europe. So you want to be able to dynamically detect where the workload is coming from and change the voters. The trivial way to do that would be to look at all your replicas and consider every subset of number of voters. For example, if you need 5 voters to be able to tolerate 2 failures, so consider every subset of 5 out of, I don't know, 11 replicas. And for each subset, use the previous algorithm to choose the best leader. This is exponential in the number of replicas. So this is not scalable. For a typical database that we had, it's about 26 million computations per time interval. So we didn't want to do that. Instead, we decided to reverse the problem. Instead of first picking the voters and then the leader, we first pick the leader and then the voters. So we consider all the possible choices of leader, and for each one, we pick the best voters, the best quorum for that leader, the quorum with the lowest latency. And this is quadratic and gives the optimal solution. It's not a heuristic. And in our case, it's 4 orders of magnitude less operations than the brute force. For some databases, we saw that this is much better than just changing the leader. Here's an example. So this is time. Sorry. This is time, and this is the blue line is just is a latency improvement when we just move the leader around. We see that we get about 10% latency reduction by moving the leader. The red line is what happens when we move the voters and the leader. We can see that we get about 35% latency reduction, which is very good. But what is perhaps surprising is that this specific database is read heavy. It has 98% of reads. The reason we were surprised is that the voters are supposed to matter for commits. Why do we get such a big improvement for reads, for a read-heavy database? And the reason is simple, is that the leader is chosen to be one of the voters. By moving voters around, we have more freedom to choose the leader in a better way. And most of the reads here actually involve the leader. So that's how we get this gain. So what about this follow the sun idea about Europe and the US? Is it really true? So turned out not to be so true, for at least in our system. This is a workload for a typical database. And the y-axis here is a percent of European traffic as a percent of the US traffic. We can see this is about 35%. So pretty much never the European traffic is more than the US traffic, even during nighttime in the US. So you don't want to move voters to the US typically, but you may want to move voters from West Coast to East Coast, as we saw for some databases. This is what our algorithm decided, and this is the fraction of West to East traffic. Okay, the last optimization tier is how do you decide on the replica locations? The intuition is that you want the replicas close to the clients, and at the same time, you want the voting to be fast. To do that, we use a variant of, so this is basically a facility location problem. So we use a variant of k-means, or weighted k-means. And the idea is that we place replicas in concentrations of active clients. But we also want the voting to be fast. So we chose these two heuristics based on k-means. One is called KQ, k-means first, quorum later. So we first place all the replicas next to the clients, and then use the previous algorithms to pick the best quorum and leader. The second option is we first pick the best quorum out of all the replicas, all the data centers that we have at our disposal. And then the remaining replicas we use to place close to the clients. So the k-means first, it's very good for read-heavy workloads, but it's not optimized for writes at all, because the quorum may be slow. The second one is very good for writes, but potentially if it's a read-heavy database, it wastes replicas for quorum instead of placing them close to the client. So which one should we use? The good thing is that our algorithms produce a latency-based score, so we can just run both of them and get the score. And we saw that the best one is usually within 5% of the optimum, which we calculated by an exhaustive search. And for 6 or more replicas, it's within 1% of the optimum. We can also use this algorithm to help decide how many replicas we need, because you can look at the diminishing returns of adding more replicas. You have the cost, so you can look at what's the optimal placement with 6, with 7 replicas, and how the cost drops, and you can decide when to stop. Okay, so before I complete the talk, I want to put this in a slightly larger context of reconfiguration, because this is what we're doing. We have a distributed database, and we're changing the replication over time. And this topic has been extensively studied in the literature. It's very subtle because you have a consistent distributed database, and you want to preserve the consistency and also the availability while changing the system. By now, most systems in production support dynamic reconfiguration, which is the mechanism of how to reconfigure. What's not so much explored is what and when to reconfigure, the policies. And this is what we try to do in this work. The most common approach probably is manual. You have an administrator that comes and says, I want this type of replication for my database, I want the replicas here and there. And this is just not scalable. In our system, we have thousands of databases. An administrator cannot possibly be expected to do the right decision. Some systems use heuristics, which may work for one workload, but may not be so good for another. And also there have been recent solutions for doing this in brute force. And this just doesn't work for a Google scale. So instead, we have a workload-driven solution that dynamically adjusts replication for this database. And to sum up, we showed that determining the right replication policy is important. It significantly reduces latency in our system. Manual and brute force approaches do not scale, and heuristics only work for some workloads. So our workload-driven optimization has a caveat, because we use Google's monitoring infrastructure, which is global and gives us all the information that we need to do the optimization. For example, in the Yahoo Peanuts paper, they were saying we use local heuristics because achieving such global information is just not possible. So we do have that information, but it's not, we don't have everything we want. So we have some information, but for example, we didn't do optimization in a sub-database level because we just did not have the monitoring, and it was not feasible to add it. So there is some limitation to the monitoring. And we have an optimization pipeline working with one of Google's distributed databases. Thank you very much, and I'll answer any questions. Yeah.
So I have two questions. One, just clarification. What are your clients? Are your clients stationary or they're mobile?
This is servers in a data center.
Servers. So
Yeah.
And the other, is any of those are spanner?
Is what?
Are any of the databases are spanner?
I actually cannot say what the database was. It's a one database that we optimize, but I'm not. I cannot say what it was. Yeah, Eddie?
Did you try to measure the short-term effect of moving the leader or the routers around?
Yeah, so it's a trade-off, right? So you can have there are patterns that you can take advantage of. If you move the leader quickly, there may be patterns that you can take advantage of, like this day and night time. On the other hand, you don't want to react to workload spikes. So it's a trade-off and how to do this. We didn't really explore how to do this optimally. We try to exploit the trends, but not to be overly sensitive to the spikes. Yeah.
You seem to be assuming that there's no queuing delay. Is it indeed
Yeah.
like below that?
Yes, so we do assume that the processing latency at the nodes is 0. In our system, we saw that it's okay. Obviously, this is not perfect. We model the latency based on the network latency. But since this is over 1, the network latency is dominant. It's dominating the operation latency. So the queuing latency, if it exists, it's much smaller than the 1 latency. Yeah.
Why single leader and not multi-leader?
Well, there actually are multi-leader because each database is sharded, and there is a single leader per shard. Actually, in a single database, there could be 1,000 leaders, even more.
But you need multiple voting, is that convention?
Yeah, every shard is voted upon separately from the other shards.
So you still have to run consensus over one for a single piece of data, right?
Well, it depends on the database. Yeah, in our specific database, yes.
So why like approach like multi-boxes and not like key boxes or things like that? There was a reason. I mean, just one.
No, I haven't designed. We didn't design the storage system. We just worked with the production team to optimize it. Basically, the decision of which Paxos variant to implement was not ours. Yeah.
So, should the system converge in case of using multi-pass workload for application statements, best TCP or something else, or inclusion of conversion is when you have different links at the same time and with slightly different lenses?
I'm not sure I heard this.
Okay, so the question is, if you have constantly changing latency on the link, should the system always converge?
Yeah, so we monitor Google monitors the network latencies, and we use it. We do some kind of an averaging. So we don't look at these jumps. We look at latencies and time intervals. So it depends actually what you're trying to optimize. Since we're optimizing for the average, we're looking at average latencies. If you're optimizing for the tail, you need to look at the latency distribution and work with that. We show in the paper how to do that, but in production we implemented the optimization for average latencies. Yeah.
All the smart questions have been asked, so here's a stupid one. For example, you mentioned facility location, and in fact, for several of those problems, there's a lot of research in the optimization community about this kind of things. Even, for example, again, facility location is well known, but with this cost and that cost and so on. And in the end, what I see is that you either use exhaustive search when you can, you flip the problem and have an optimal quadratic search when you can, and when you can't, you use the heuristic k-means followed by this. Have you tried any of the facility location optimization algorithms that are designed to provide a good approximation?
We are trying them, but not for this work. For this work, we tried exhaustive search. Exhaustive search took more than a day for a small database.
Obviously not. I mean,
no,
approximation algorithm.
we haven't tried it for this work. But we realize this. What you're saying is true, of course. But the good thing about this heuristics.
It works. It's
So
great.
for the first two optimization tiers, we get an optimal solution, right?
Yeah.
For the third one, the algorithm runs in seconds and gives you within 1% of the optimum. So we didn't really have a good incentive to explore this further, but of course, yeah.
Thank you, Alex, for the good talk. Thank you.